live. Okay. Apologies for starting late, and I have not rehearsed anything that I'm going to show now. I'm not live. Hello. False start, I think. I left the YouTube playing. I've not rehearsed what I'm going to show. This is going to be mainly a huge thought experiment. And unlike Martin Lidke, who obviously rehearses everything that he does, I have not rehearsed anything. So this is about the sun. So first thing, while I make a roll up, I'm going to screen share a portion of the video I did about the map. And the purpose for it, I'll talk through it. God, aren't you lucky? Let me make sure that I'm screen sharing. Yes. So the purpose of this is to start to explain the motion of the sun. Here we are in a room. This is in Dubai somewhere, but that's not important. And the light is a lamp. So this person is facing away from the light, is seeing the reflection. Okay, we all totally understand what's going on there. Now, I'm going to pause in a second, and I'm going to, I discussed this with Dr. Zach earlier today. We're going to some interesting realizations. Okay, so picture that you're standing in that room and you have a pointing stick like I have, okay? And you point at the sun right now and you touch the lamp, this skylight lamp, in the center of the sun, and you keep that pointer there. Now, over to your left, somebody else here gets their pointer and touches the center of the sun. And the truth is, there's going to be 2 feet difference between where the pointers are touching the screen. So the sun is not in 2 different locations. What's happening is there's an optical illusion that's presenting the sun from 2 different locations to 2 different viewers. And this is the problem that we have when trying to measure distances and measure time with the sun. So measuring distance like elevation from the ground with longitudes or latitudes. So again, picture that you're touching the screen. Let's say you're touching the screen with your finger and you keep your finger there, and the person over to your left, let me scroll back, the person over to your left does the same. Now, this is important. These lamps, the sun, the thing that appears like the sun, is not 30 meters above this. It's about 50 centimeters above the lamp, above the screen. So this is the screen, and this thing is 50 centimeters. The reason it displays parallax is the effect of the gases, not a standard perspective phenomenon. Okay, so let me stop screen sharing. Oh, okay, here we are. Oh, yeah, I think I was sharing. Maybe I should have rehearsed. 1 second, guys. I'm going to ask in the chat, did that play? Yeah, it did. Okay, I can see. Okay, so we're looking at the sun. We're working with a map. So we're working with the physical world, and we have people in, say, India and in Egypt, both looking at the sun. And what they're going to see is the same as the 2 people looking at that lamp. The difference is going to be the angle between the person in Egypt and the person in India. But they're still putting their finger in the middle of a sun that is not the same position as the other person. So exactly the same as that lamp, okay? So the angles, they're not quite irrelevant, but they do not help to discern where the sun actually is. Now this is what I'm thinking. You're gonna have to bear with me for this stark light. I'm thinking the sun is on a track. Let's call that track the sun ring, and it behaves like a physical ring. In other words, if you have a ring and there's a glint in that ring, so there's a light reflecting on that ring, you can point to that light, and a partner or a colleague somewhere else can point to that light too, but they'll be pointing somewhere else. The same light will appear to be somewhere else to somebody else. It's based on your orientation to the ring on which the light is glinting. So I've developed this tiny little experiment. This is similar to experiments that were done months ago by a variety of different people. I want you to pay attention to this here, okay? All I'm going to do is move this around and you're going to see it move, okay? Now the point of this is, just as you, which are all sharing the same perspective right now, which is my one-eyed camera perspective, are all seeing it at the same point simultaneously. But if you were here and you all pointed to where the light was, because you can't share the same space as another observer, you'd have to be at least shoulder width apart or head width apart if you were lined up in a strange configuration. But this would be in a different position to all of you at the same time. And this is what the sun seems to be doing. It seems to be on a circuit that oscillates, and its oscillation causes the appearance of the sun to be in different locations to different people. Ooh. And that's why the protractor gives us false readings. Because, let me pull the protractor thing. 1 second. Whistle for yourselves if you want. Silly me, I have it right here. Okay. This problem with the protractor, okay? These guys can look at the sun. So let's say that there's 1,000 miles between these two distances, okay? For the sake of argument, let's say that 15 degrees displays 1,000 miles of difference, give or take. And this person can see the sun overhead, and this person can see the sun in the same relationship as this one has to this, only reversed. So let me get my pointer. This person, at the same time this is, okay, this person sees the sun directly overhead, and this person who's standing here sees the sun there, okay? This is what we would logically conclude, but this is not so. This is a falsehood. This is a logical error that we've arrived at because we've relied on the protractor. And just by looking at the rest of the times on the protractor, we can discern that this is a logical error, okay? This guy can see the sun right above his head, whilst this guy, who's standing here, might see the sun here. We don't know. And this guy can't discern where this guy is seeing the sun. So if this guy's orientation to the sun was exactly the same as this guy's at the same time, in other words, this guy's looking straight up, the sun was local in the sky, and this guy had to lean his perspective over this way to see that same sun at the same time. If that was the case, then these guys would have to do likewise for the same sun, which means whilst this guy is looking at the sun here, and this guy is 1,000 miles away, and this guy's just over 1,000, and just over more and more, this guy is seeing the sun at an angle that tells him that he is, well, 1, 2, 3, 4, 5, 6, 7,000 miles away. But if we count the thousands of miles here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, just over 10,000 miles. This is an error. Now, what this guy is going to see when looking at the sun, or this guy, is going to see the sun at some position that does not relate to the position where any of these guys see the sun. It's based on that person's orientation to the sun, the same as with this bowl. Okay? So the reflection that you saw on this bowl that moves around, okay, it's also, I noticed something when I was doing this, okay? If we look at this reflection here, okay, this also moves. Now, I'm not saying at all that there's any physical ring in the sky or any glass dome in the sky, okay? But this, the movement that you see, so now it's going lower, now it's going higher. This movement, as well as this movement that you see, this sideways movement, okay, you'll notice that not only does it move sideways, but it also moves down. Now, I'm not moving this down. This, I'm going to keep this at the same point, but the light is going to go higher. Look, I've tried to keep this at the same point, okay? And it seems that this is what the sun is doing. Now, from your point of view, you will have seen an arc, a curve. But on this, what's happened is it's done a circle movement, because this is a bowl, you know, there's no tricking this, okay? In fact, it's made an oblate circle or track. So when we're looking at the sun, trying to establish its elevation from the earth and its movement across the sky, if we rely on misconceptions, which are they're actually logically sound misconceptions, if that's even a thing, we can logically deduce something false. This tells you that we can deduce logically and correctly, we can deduce something having followed all of the rules of logic that render a false result. So this, one way of explaining this, if you'd like to explain it to anybody else, is with a rainbow. Okay, this is my rainbow example. No, there's no colors. Okay. This is a rainbow. The observer, you, anybody else, is for this example is looking due north. Okay, you're looking due north and you're seeing an arc. Somebody else is looking at it too. They're looking at it from this direction. So their orientation to the rainbow is northeast. However, they are still seeing this. It's not a case that whilst you're seeing this, that's what's being presented to them, or while they, looking northeast, are seeing this, sorry, they're seeing this, that you would have this presented to you. No, you're going to continuously see an arc. as you look at the rainbow. This is a bubble, a quick drawing of a bubble, okay? If you remove the tiny little reflection mark that I made, if this is very clear bubble, all you're really going to be able to discern is the boundary, the edge of the bubble. But the bubble is round. It looks like a curve, like an arc, but it's round, and your depth perception will tell you. So this is what's happening with observers looking at the rainbow. This is the orientation between this observer and the rainbow, okay? He's looking directly north. This is a bird's eye view, a top-down view. It's looking directly north, and the rainbow presents itself at right angles to his point of view. Now, this person looks at this same rainbow, but what they see is at right angles, so perpendicular to them. So this person sees that line, I think that might be just slightly off perpendicular, at right angles. This line, they see at right angles. This guy sees this at right angles. It's the same phenomenon. It's the same rainbow. It's in the same field, okay? But if you try to go and measure your distance, the distance between you and the rainbow, you won't be able to arrive at an actual distance, because a rainbow is a visual phenomenon. And the nearer you get to it, the wider it's going to get. And when it gets to a point where you might be able to discern its location in terms of distance, it will no longer be there. Not only that, but it will have remained in front of you as you move towards it. It will have remained in front of you without displaying the normal movement of objects. So this is it pretty much. This is something that I wanted to cover, because when you're working with maps and you're working with distances, then you're combining logical concepts with empirical evidence, okay? We have empirical evidence that islands rest in water, for instance. We know this, okay? They don't move around, you can't pick them up. Islands are something physical, and they're surrounded by water. That's what an island is. And there's a distance between that island and the nearest coastline. And there's a separation of ocean or river or whatever, okay, lake maybe. And that's fixed. We're going to ignore tides for now, okay? But you have an island, you have a coastline, and you have a set distance. This is empirical. We can test this. We can physically test this, okay? However, how the sun travels over that coastline to that island, even though we have empirical evidence of the sun existing and sunburning you and casting shadows and moving, we cannot deduce empirically where that sun actually is, because the nearest thing we can do is use tools to try to arrive at a conclusive number, a distance. And we don't have those tools, and the sun is not in one physical location. In fact, the sun is not in any physical location. The sun is simply the same way as a rainbow. A rainbow is not physically at a location. It does not have physicality. It doesn't have locality. It doesn't have a portion of space that it inhabits. It exists, but it doesn't inhabit space. So the same with the sun. So you have somebody on an island and somebody on a coastline, and this guy looks up at the sun, and this guy looks up at the sun, and we can deduce wrongly, that their line of sights converge at a point. But they're seeing the bottom of a ring. They're seeing a circuit. They're seeing the same phenomenon as with this. Yes, it moves, but where they each see it is different. They will not point to the same point in space. When the guy in the coastline points to it, he might point here, while the girl in the island points to it, she might point to it here. And those lines don't have to converge. In fact, for all we know, she might point to it here, whilst this guy points to it there. That's it. I hope that helps some of you with opening the range of ideas you'll play with. That's it. Thank you very much for your time, and thanks for watching.